In this segment, we'll talk about the LU decomposition method, the basis of it. So to talk about the basis of the LU decomposition method, we need to recall what we are trying to do in the first place. So what we are trying to do is we are solving a set of equations. So let's suppose n equations, n unknowns. And then we know that this is the coefficient matrix. And this is called the unknown vector. Many times called the solution vector. I like to call it unknown vector because we don't know it yet. And of course, it's a solution vector once we know what the solution is. And this is called the right-hand side vector. So we want to be able to find out what this unknown vector is. That's the bottom line. What LU decomposition basis is that, hey, one can write the coefficient matrix, the square matrix, which is the coefficient matrix here, as in a form of L times U, where L is the what we call as the lower triangular matrix, and U is called the upper triangular. And people might say that, hey, can we always write A in LU form? It's a little bit not a difficult question to answer, but we cannot do it clearly. One of the things which I can tell you is that if A has an inverse, or what we call as a non-singular matrix, then you can surely write it in some form which looks like this, where this P is a perturbation matrix. And this P could be the identity matrix, and then it'll be just in this form. But sometimes you might have to use the perturbation matrix to be able to reduce the coefficient matrix into an LU form. So we're not going to get into this discussion at this time because it makes it a little bit more complicated. So we're going to stick with this, that, hey, you have an A matrix and you're able to decompose into L times U. So how does that help us to find the solution to the set of equations? Let's go and talk about that. So as you can see that we are given AX is equal to C, and then we're also saying that, hey, somehow we know what the LU decomposition of the matrix A is, and that's what it is. So what we're going to do is we're going to substitute this into here. We're going to say L times U times X is equal to C. And now what I'm going to do is I'm going to multiply both sides by L inverse. That's what I'm going to do. And the reason why I'm allowed to do so is because we already said that, hey, A is a non-singular matrix, and that's the only thing for which we are talking about the LU decomposition method. So if A is non-singular, then L and U also have to be non-singular. It can be proven. So that's what gives us the capability of multiplying both sides by L inverse. But what is L inverse times L? It is just I. And what is I times U? It is just U, as per the definition of identity matrix. So we get this. Now what we're going to do is we're going to say, hey, let U times X be equal to Z. Say. So we're not saying that it's equal to some known quantity Z. We're saying, hey, it'll be some vector Z, because it's an n by n matrix. This is an n by 1 matrix, and it's an n by 1 matrix. So if that is the case, if Ux is equal to Z, then what we have is that L inverse times C will be equal to Z also. And I can multiply both sides by L now. And let's see, what do we get from doing that? L times L inverse is the identity matrix. Identity matrix times C matrix is just the C matrix. And you get L times Z. And what I'm going to do is I'm going to just write it down here. We get L times Z equal to C. So what you're finding out here is that you're getting two sets of equations. Two sets, not two equations, two sets of equations, where you have this and this. So you can very well see that what the basis of the LU decomposition method is that, hey, let's go and solve this first, because we know what the C is. We know what the right hand side vector is. We know what L is because we've said that, hey, we know what the LU decomposition of the A matrix is. We can find out what Z is. And once we have calculated Z, we can plug it back in here. And since we know what the U matrix is, because we already said that, hey, we know the LU decomposition of the A matrix, we can find the value of X. So it's a two-step process. You have to first solve L times Z equal to C, and then you have to solve UX equal to Z. So let's go and summarize this. So in summary, we are trying to solve AX equal to C. We already know what the LU decomposition of A is, and we end up with two sets of equations. We say LZ is equal to C, and then we say UX is equal to Z. So this becomes the first set of equations, this becomes the second set of equations. So what you're finding out is that you have a lower triangular matrix multiplied by unknown vector Z will give, and C is the right hand side vector, will allow you to find Z. Once your Z has been found, you have U as an upper triangular matrix, and you can find the value of X. So let's go and see that how does it work for, let's suppose, a 3 by 3 matrix. Not through an example, just to give you an idea that, hey, how it makes it easy. So if I had a 3 by 3 matrix, so I have L times Z equal to C, which I have to solve first. So the lower triangular matrix, let's suppose 3 by 3. So I'm just taking an example here of a 3 by 3, 3 equation, 3 unknowns. And I'll have Z1 here, Z2 here, Z3 here. And the right hand side also will have 3 elements in it, like this one. You can very well see that when I look at this set of equations, in the first equation, I only find out that, hey, Z1 is the only unknown because 0 will get multiplied by Z2 and 0 will get multiplied by Z3. So I'll have, from the first equation, I can find Z1. Now, if I look at the second equation, what's going to happen is that it will get multiplied, Z1 will get multiplied by a non-zero quantity, Z2 will get multiplied by non-zero quantity, and Z3 will get multiplied by 0 right here, but I already found Z1. So since I already found out Z1, it's only one equation, one unknown, where I can find Z2. Same thing let's do for the last one. The last one, non-zero numbers are getting multiplied to Z1, Z2, and Z3, but we already know Z1 and Z2, so that means that we're going to solve only one equation and one unknown to find Z3. So you're finding out it would be very similar to what we talk about the back substitution method in our Gauss elimination. So the only difference is that this is forward substitution, and that is the first step of LU decomposition method. Let's go and see that, hey, what happens when we have the second set of equations, which is UX equal to Z. So let's look at the second set of equations, which is UX equal to Z. And we just found out Z from the forward substitution, so we want to be able to find out what X is. Let's take an example of 3 equations, 3 unknowns, and see how that works out. So we'll have non-zero elements here in the upper triangular matrix, possibly, but surely 0 elements right here in those locations. And then we have 3 elements in the unknown vector, and then just we have found out what the Z vector is, so we'll know these 3 numbers on the right side. But if you start from the back, you start from the last equation, you find out that, hey, this last equation has only one non-zero element here multiplied to x3, so that will give me x3 directly. Now, if I look at the second last equation, although this is getting multiplied to x2 and this is getting multiplied to x3, which are non-zero elements, but I just found out x3, so I can find out what x2 is. Same thing here. X1, x2, and x3 are getting multiplied to non-zero quantities, but I already know what x2 and x3 are, so that allows me to solve only one equation, one unknown at a time, just like the previous ones, and I find x1. And this is nothing but back substitution, which is exactly the same algorithm which we use for Gaussian elimination, whether it was a naive Gaussian elimination method or whether it was Gaussian elimination with partial pivoting. So that is the basis of the LU decomposition method, how it works so far as solving a set of simultaneous linear equations is concerned. And that is the end of this segment.